Okay, so now we are going to start talking about basically like patterns in numbers, and specifically those patterns are represented as what we call sequences. So there's two main kinds of sequences that you need to be aware of. There are other kinds of sequences, but the two main kinds we're going to focus on are arithmetic sequences and geometric sequences. Arithmetic sequences are patterns with a common difference, which basically means you're either adding by the same number over and over or subtracting by the same number over and over. So look, as you go from 2 to 4, you're adding by 2, or 4 to 6, you're adding by 2, 6 to 8, you're adding by 2. That common difference then is 2. Technically, what you should do if you want to find the common difference, take a number and subtract the previous term. That's why it's called the common difference. 4 minus 2 is 2. 6 minus 4 is 2. 8 minus 6 is 2. Okay? In my second example, 10, 6, 2, negative 2. Again, you have to think about what are you constantly changing by. We're minusing 4 and minusing 4 and minusing 4. Another way of figuring out that the common difference is negative 4, 6 minus 10 is negative 4. 2 minus 6 is negative 4. Negative 2 minus 2 is negative 4. A number minus the previous number is the common difference. If I now want to be able to write an explicit rule for what we call the nth term, so any term in the entire sequence, this is the rule that you need to memorize. A sub n equals a1 plus n minus 1 times d. A1 is talking about the very first term that's in that sequence. So for example, if I wanted the nth term rule for the first sequence I have, 2, 4, 6, 8, A sub n equals A1, which is 2, plus, you would leave it as n minus 1, and then you'd put after the n minus 1 multiplied by 2. So therefore, for example, if I wanted to find like the 10th term of that sequence, instead of sitting here and adding 2, adding 2, adding 2, if I want the 10th term, I do 2 plus 10 minus 1 multiplied by 2, and now I know that the 10th term is 20. Or the 100th term, 2 plus 100 minus 1 times 2 is 200, and now I can get the a term in the sequence without having to know all the previous terms. For the second example, same idea. A sub n equals A1, which is 10, plus n minus 1 times the common difference, which in this case is negative 4. So it's like a decreasing thing, if you will. If I want, again, the 10th term, I would do 10 plus 10 minus 1 multiplied by negative 4. And then it would come out to be negative 26. It should hopefully make sense that as I keep minusing 4, I should getting more and more into the negative values. You should know arithmetic sequences are really linear functions. Okay, linear functions where that common difference is actually the slope of that linear function. Okay, so just so you can keep things connected in your mind, arithmetic sequences are linear functions. Geometric sequences, on the other hand, are actually exponential functions. Okay, you are constantly multiplying by the same thing over and over and over again. And so you'll see behavior like the exponential functions like we were talking about in some of our previous lessons. So a geometric sequence technically is a pattern with a common ratio. So as you look at something, you're going to say, okay, in this case I can see that I'm timesing by 2 and timesing by 2 and timesing by 2, so my common ratio is 2. Another way you could figure out that common ratio is to do a number divided by the previous number. 4 divided by 2 is 2. Okay? 8 divided by 4 is 2. 16 divided by 8 is 2. Like, for example, in the second number, you're not going to think of something that you're dividing by as the common ratio. In this case, to get the common ratio, take the second number and divide by the previous number. 27 divided by 54 comes out to be 0.5 or 1/2. Okay, and I just realized, I just made a mistake on this one. 27, so let me fix this. 27 times 0.5 should be 13.5. So let's make this 54, 27, 13.5, and we'll just leave it like that, okay? And so therefore, if I want to check the common ratio again, take 13.5, divide by the previous term of 27, so 13.5 divided by 27, and you'll see that that also comes out to be 0.5 or 1/2, and that's what makes it have a common ratio. Okay, so now if I want to write the rule for this sequence, here's the explicit rule for a geometric sequence. And the good thing is I'm pretty sure this one is on your reference table if you were to take the final or the regents. So I'm going to have A sub n equals my first term, which is 2, times my common ratio, which is 2, raised to the n minus 1. So therefore, like I said, if I want a term of this sequence, I do 2 times 2 to the, let's say I want the 10th term, 10 minus 1. You'll notice that this gets much bigger than the linear one did before. Exponential functions, if you remember, get really big really fast or really small really fast, depending on if you're increasing or decreasing. With the next one, my a sub n rule would be a1, which is 54, multiplied by 1/2 to the n minus 1. So let's say I want the 10th term here, 54 times 1/2 to the 10 minus 1. And you'll see that comes out to be a really small number. This is a decreasing exponential function because the growth factor is less than 1. And you can see that it gets really small really fast. And that's because geometric sequences are basically exponential functions. So as you take a look at these next 3 sequences, determine if it's arithmetic or geometric. If you can, write an explicit rule for the nth term and find the next 3 terms. So as I look from negative 32 to negative 62, negative 62 to negative 92, it looks to me like I'm subtracting 30. Now if I'm not sure, remember I said common difference, you can take a number and subtract the previous number. Negative 62 minus negative 32 comes out to be negative 30, and that's how I know that this is my common difference. I'm adding or subtracting by the same thing each time, so common difference is negative 30. So my a sub n rule for arithmetic sequences is a1 plus n minus 1 times d. So a sub n equals a1, which is negative 32, plus n minus 1 times negative 30. I don't really have to plug into my formula to get the next 3 terms. It's easy to just take negative 122 and minus 30. So my next term would be negative 152 minus 30 would be negative 182, and minus 30 would be negative 212. Okay, so it's pretty easy when you want the next 3 terms. But if you wanted something like the 40th term, this is when the explicit rule would be helpful. Okay, number 2. As I go from negative 4 to 12, I'm adding by 16. As I do 12 plus 16, I'm not getting to negative 36. So this seems to me like it's maybe more of a geometric sequence, I should mention. This is arithmetic because of the fact that I have a common difference. Okay, so if I think it's geometric, that means it probably has a common ratio. To figure out the common ratio, you take a number and you divide by the previous number. 12 divided by negative 4 is negative 3. Is that the case if I divide 2 next numbers, I guess you would say in the sequence? Negative 36 divided by 12. That also comes out to negative 3. So the fact that I have a common ratio, that's why this is geometric. To make the nth term rule for a geometric sequence, the rule is a1r to the n minus 1. A sub n in this case then is a1, which is negative 4, times r, which is negative 3, raised to the n minus 1. Make sure that negative 3 is in parentheses. To get my next couple terms, just like I did in the previous one, I'll just keep timesing by negative 3 instead of minusing by 30 like in the last one. 108 times negative 3 is negative 324. Okay, times negative 3 is 972, and times negative 3 is negative 2916. And as I said before, you should expect that you're going to get really huge numbers or really small numbers as you work with a geometric sequence, because that's what happens with exponential functions. Okay, so let's take a look. As I go from 1 to 2, I'm adding by 1, and then I'm adding by 4, and then I'm adding by, I don't know, 18, I think. Definitely not arithmetic, okay? Geometric, am I dividing by the same thing? So if I do 2 divided by 1 is 2. If I do 6 divided by 2, that's 3. I don't have a common ratio. I don't have a common difference. This is an example of one that comes out to be neither, okay? If it's neither, you don't have to write a rule for it. You just say that it's neither. Okay, so sigma notation is a shorthand notation to represent the sum of a bunch of terms in a sequence or in a series. So what happens with sigma notation, you're going to start with something like n equals or k equals or I equals or something like that, okay? Let's say it started with n equals 4 and goes up to, 9. What happens is you're going to start by plugging in 4, then you're going to plug in every integer from 4 up to and including 9, and what are you going to plug them into? You're going to plug them into some function inside your sigma, which I'll call f of n for right now. Okay, so this is your starting value to plug in. This is your final value to plug in. Okay, and you're plugging them into whatever function you have inside your sigma. So for example, if it says express as a sum, you literally just have to write out what things are being added together. So this is an example of one where, okay, I'm going to start by plugging in 2. This will be 2 squared. Now I'm going to also do every integer between 2 up into and including 5. So 2 squared, 3 squared, then I plug in 4 squared, and finally 5 squared. And that's it. I just have to write it as a sum. If I wanted to do anything else, I could make it like 4 plus 9 plus 16 plus 25. But again, you're just expressing it as a sum to get used to how the sigma notation works. With number 2, you're starting with n equals 3. So you'd be plugging in and you'd be doing 2 times 3 minus 1, okay, plus, so maybe we'll put that in parentheses, okay, 2 times 4 minus 1, plus 2 times 5 minus 1, plus 2 times 6 minus 1. Okay, and if I want to clean that up a little bit, what is that? That's 6 minus 1 is 5, plus 7, plus 9, plus 11. Okay, again, right now you're just expressing it as a sum. When it starts saying evaluate, that's when you start adding those values together. And I'm going to actually show you both by doing it, how to do it by hand and how to do it in the calculator. So if I have something like n plus 3, I'm going to be adding 1 plus 3, 2 plus 3, 3 plus 3, 4 plus 3, and 5 plus 3. Okay, and right now you're not just writing it as a sum, you're actually going to evaluate this. Notice that each time I replace down with one of the integers from 1 all the way up to 5, including 5. So 1 plus 3 is 4, 2 plus 3 is 5, 3 plus 3 is 6, 7, 8, and now I just add these together. 4 plus 5 plus 6, 4 plus 5 plus 6 plus 7 plus 8 comes out to be 30. Okay, not only am I going to show you how to do it in the calculator, but in our next lesson we're going to talk about using a specific series sum for this. This is, by the way, what we would refer to as an arithmetic series. And the reason why is because if you look at the pattern of numbers, 4, 5, 6, 7, 8, see how you're going from 4 to 5 by increasing by 1? Increasing by 1, increasing by 1, increasing by 1. That's because this is actually an arithmetic sequence where we're adding the terms together, hence why we start to refer to it as an arithmetic series. Okay, so a series is when you take the terms of a sequence and add them together. So if you take a look at the next one, 2 to the n, this would be 2 to the 1 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4. Okay, so that's really 2 plus 4 plus 8 plus 16. When I add those up, that adds up also to be 30. That's funny. Okay, and so when I add those together, that's my sum. What you've actually just found right now is the sum of what we call a geometric series. The reason why is because this is actually a geometric sequence, 2, 4, 8, 16. It's a sequence with a common ratio of 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So again, that's why it's a geometric pattern, but because we're adding the terms of that pattern together, that's why we refer to it as a geometric series. So now if I want a way to be able to check that this is 30 or check that this is 30, what you can do is you can go on your calculator and you can hit the math button, scroll up from the bottom to where it says summation, and you'll see the sigma notation come up just like you did before. So x equals 1 to 5, so you make sure you type in the numbers you have. You'll have to type it as x instead of n, but it's the same idea, and you can see that comes out to be 30. Once more, math, come up from the bottom, summation. This is going from x equals 1 up to 4, 2 to the x, and that also comes out equal to 30. Okay, so we had to express as a sum, we had to evaluate whether by hand or in the calculator, either one is fine, and then the last thing is be able to take a specific series and represent it in sigma notation, and what we're going to be using here are our arithmetic and our geometric sequence formulas. Okay, remember a sub n equals a1 plus n minus 1d, or a sub n equals a1r to the n minus 1. What you're going to do is you're going to identify what kind of pattern do you have, make a rule for that pattern, that's what goes inside the sigma, and then basically figure out how many terms you're working with in these problems. So as I take a look at the sequence that goes with this, 1, 3, 5, 7, I can see that I'm constantly adding by 2. So that means I have a common difference of 2. My A1 is 1. So if I was making my nth term rule for that, A1 is 1 plus n minus 1 times my common difference of 2. Okay, so when I set up my sigma, I'm always going to start with n equals 1 when I create it myself. That's because we start with A1, what happens when you plug in n equals 1. We'll talk about finding what the upper value is in a second, and then we take our an value without the actual an and we put that on the inside. 1 plus n minus 1 times 2. You may see some situations where this is like distributed and like terms are combined, but I would be fine if you just left it just like that. That's fine. So the question is, what is my upper bound? Okay, so you can do one of two things. You can plug this in the calculator and find out when it's equal to 21, or you can just solve it by hand. 1 plus n minus 1 times 2 equals 21. If I minus 1 from both sides, this gives me 2 times n minus 1 equals 20. Divide both sides by 2, so this gives me n minus 1 equals 10. And as I add 1 to both sides, this tells me n equals 11. And then 11 then is my upper bound for that sigma. You'll notice within the next example, you don't have to worry about that. It actually tells you what the n value is in example number 6. So the question is, arithmetic or geometric? Look at the pattern of numbers. -1, 3, -9, 27. You're constantly multiplying by -3. So our common ratio is -3. This is now a geometric pattern. So a sub n equals a1r to the n minus 1. So a1 is -1, r is -3 to the n minus 1. So our sigma looks like this. N equals 1 to 8, because they told us it was 8 this time. A1, r to the n minus 1. I should point out, think about order of operations. Parentheses, exponents. I would have to evaluate this exponent before I multiply or divide, so you should not actually be multiplying the -1 and the -3. You leave it just like this. Okay, so the series sum formulas. So this is for a situation where like maybe you could plug it in your calculator, maybe you can't. There are some formulas that are provided to you on your reference table, so you don't even have to worry about memorizing them. You just have to know when you're supposed to be using them. So either it's going to tell you this is a series. It would have to tell you that it's arithmetic or geometric, or we'll talk about how you can be able to determine it by looking at the equation. So arithmetic series. Arithmetic series is going to use the arithmetic series sum formula. So in this problem it says to you, you have n equals 15, your first term is 22, your last term is 120. So to find the sum of the terms of this series, so I'm not actually showing them out, but if I did, if I was adding up all the terms of a series similar to what we were talking about in our previous stuff, this is the formula I would use if I wanted to find it without having to sit there and add everything up by hand, like we were talking about with the beginning of sigma, or without using my calculator. So in this case, your sum is going to be n over 2. Okay, I'm using this formula right here. A1, which is 22, plus an, which is 120. So I would do 15 divided by 2, 20, is it 20? No, it's 22, plus 120. And that adds up to be 1065. And now you have the sum of all the terms of that series, all 15 terms. So number 2, how do you know if it's an arithmetic or a geometric series? Well, remember what I said before? Arithmetic sequences are really linear functions. Arithmetic series are really adding terms together of an arithmetic sequence. So if it looks like what's inside is a linear function, that's how you can tell that it's actually an arithmetic series. So how would you use the formula to be able to do that? Well, what you need is the very first term, A1. You need the last term, which is going to be A35. That's going to be like your AN. And you're also going to need your N value, which is a little weird. It's top minus bottom plus 1. So 35 minus 1 plus 1, which tells you there are 35 terms. A1 is 6 times 1 minus 9, which is -3. A35 is 6 times 35 minus 9. So 6 times 35 minus 9 is 201. Yeah, 201. Okay, so now we're using the same formula we just used in the previous problem. Your sum formula for an arithmetic series is first term, which is -3, plus the last term, which is 201, okay, multiplied by n over 2, 35 divided by 2. So 35 divided by 2 times negative 3 plus 201 comes out to be 3465. Okay, so if you wrote out every term of that series, which I'm sure you don't want to do with 35 terms, you could easily be able to figure out the sum by using this formula. So finally, what happens if you have a geometric series? Well, once again, it's just a formula. You do have to be a little more careful with this one to make sure you're plugging things in the right spot. So I have A1 is 4, R is 2, N is 8. Okay, so I have my sum formula is A1 minus A1R to the N all over 1 minus R. I would definitely suggest you use alpha y equals for this. Type things in exactly as you wrote them. So 4 minus 4 times 2 to the 8th all over 1 minus 2. Comes out to be a total of 1020. Okay? And last but not least, number 4. So number 4, how do I know that this is geometric? This is an exponential function. If it's an exponential function, that's how you know that it's a geometric sequence, or in this case with the sigma, it's a geometric series. So that's how you know you're going to use this formula. So we need what's our A1, what's our R, and what's our N. Our A1 is 4 when I plug in the bottom number. 1 minus 1 comes out to be 4 to the 0, which is 1. My common ratio is actually the base of that exponent, which is actually 4, or you could figure out some of the next couple terms and then do a term divided by the previous term. N is top minus bottom plus 1, so N equals 10, and now I plug into my formula. A1 is 1 minus A1 R to the N all over 1 minus R. So again, with the alpha y equals. So I have 1 minus 1 times 4 to the 10th all over 1 minus 4. Comes out to be a huge number, as I said before. Exponential functions grow really big really fast, really small really fast, so expect pretty large or pretty small fraction numbers when you are working with a geometric series or sequence. Now last but not least, questions like 2 and 4, remember you can check these easily by using the summation thing in your calculator. So hit math, scroll up from the bottom and click summation. So this is x equals 1 to 10 of 4 to the x minus 1. Make sure you use parentheses if you don't have the nice calculator where I have the exponent obviously as x minus 1. And what do you notice? I get the same answer I got by using that series formula. So if you want to use your calculator, if you can make that work, absolutely do it. But just keep in mind that's what these formulas are for, to be able to do it if your calculator cannot.